All right, let's take a look at this question here. We're going to look at another optimization question. This is a cylindrical can, and we're noticing that the cylindrical can is 10 cubic meters. What's going on here is we know that the top and bottom of this can costs about $20 per square meter to construct, and the side cost is $15 per square meter to construct. We want to find the dimensions that give minimum cost. So I'm looking to minimize the cost of this question here. So first of all, let's do a quick diagram of what this looks like. So we've got ourselves our cylinder here looking something like this. And what we know here is I do not know the height, and I'm going to label the radius of this with an R. What I do know is the volume of this expression is going to be equal to, again, when you calculate the volume of a cylinder, the volume of your base here is like the area of a circle, so that's going to be pi r squared. And you're sort of stacking this h times, so that'll give you your height. Again, you take a two-dimensional shape and you stack that length of h, gives you now your third dimension volume, and we have the volume of the shape as pi r squared. I know from my question, I know that this is equal to 10. So I know that 10 is pi r squared h. That's our constraint. So now what they're interested in doing is we want to find the dimensions that minimize cost. So I'm looking to minimize cost of this expression. So my cost is going to be composed of two variables right now, r and h. So it's a multivariable function currently. And the cost of this function is essentially your surface area, but you have to attribute like a stronger cost to the top and bottom, i.e. 20 versus 15. So the area of the top and bottom, the area of a circle is pi r squared. And as you can see here, I have a bottom of this cylindrical can and a top. So it's going to be 2 pi r squared. That's going to represent the area of both the top and bottom of these. Because the cost associated with that is $20 per meter squared, I have to multiply this by 20. This is the amount of area in meters squared that I'm using up, and the cost associated per meter squared is 20. So multiplying that all, that's the cost of the top and bottom. Similar strategy for the sides. Now, when you take a look at the side of the shape, if you unravel this side shape here, this is wrapped around the can. If you unravel that, you're just going to be left with a rectangle. So I'll just be left with a rectangle here, where this is still my height. However, the distance from here to here is exactly the distance around this can. So again, if you visualize unraveling, and you can even get a piece of paper yourself and check it out. If you unravel this shape here, you're essentially, this length from here to here is your circumference, which my circumference, as you know, is 2 pi r. So therefore, the area of the side is going to be 2 pi r h. And again, multiplying by the cost for the sides is 15. So now I have my cost function. Again, the issue here is this cost function is multivariable. We got to reduce this to one variable so I can take my derivative. So I'm going to go ahead and use my constraint here. So if you take a look here, I can isolate for r or h. I would isolate for h in this question. It makes the math a little bit easier. You're avoiding taking the square root. And you'll notice I only have one h as opposed to 2 here. So I'm going to go ahead and isolate for h, in which case I get 10 over pi r squared. And I'm going to substitute that into my expression here. So now we're going to have c at r. So function one variable now is going to be 40 pi r squared plus 30 pi r, and get rid of that h and write 10 over pi r squared. So again, we can assume here that r cannot be 0. You can't have a 0 radius. It won't satisfy your volume condition. So this is going to be 40 pi r squared plus 300 over, and again, if you take a look here, the pi's will cancel and one of the r's will cancel. This will be 300 over r. So now I'm looking to take the derivative of this function here. So the derivative of this function, we're going to go ahead and take c prime at r, and c prime at r is going to give me 80 pi r minus 300 over r squared. All right, and now we can go ahead and set this equal to 0 and solve. So multiply across by r squared. We get 80 pi r cubed minus 300 equals 0. Solving for this, I get r cubed is 300. And again, here I'm noticing a little typo. This should be an 80. I put an 8. So this would be 300 over 80 pi. Therefore, r is the cube root of 300 over 80 pi. If you calculate this, you get 1.06, and that becomes our radius of our expression. And subbing this into h, you're going to get 2.27 approximately. So the area that's going to minimize our cost is a radius of 1.06 and a height of 2.27. Thank you.